In this video, we are going to be looking at interpolation in numerical methods. We will talk about the types and discuss their meaning. Interpolation in numerical methods is simply the process of determining the true value of a dependent variable, usually called entry, when a certain value of an independent variable, usually called the argument, is given. For instance, let's consider the table of values shown here. As can be seen, this is the argument and this is the entry. So the values of x are called arguments and the values of y are called entry. Also, it is of importance to know that x is the independent variable, whereas y is the dependent variable. So most times, y can also be called f of x. Okay? Y can also be called f of x since it's a function of x and depends on the value of x to be defined. So in case it's not being given as y, it can also be given as f of x. Alright. Now, let's say we are asked to find the value of f of x or the value of y when x is 2.5. Let's say we're asked to find the value of y when x is 2.5. Now you take a look at this table, you find out that there is no 2.5 on this table. Rather, 2.5 lies between 2 and 3, which means we are to employ what is called the interpolation in numerical methods. Now, let's also say we are asked to find y when x is 4.5. Again, there is no 4.5 on this table. Rather, 4.5 lies between 4 and 5, which means we are going to be employing interpolation approach to solving this problem. But then, what type of interpolation do we employ to solving this? That brings us to the types of interpolation that we have. So I'm going to mention only 4 in this video, and I'll go as far as explaining the 4 and how you can apply them to solving any problem in numerical methods. Now, amongst the types of interpolation, we have highlighted 4. We have the Newton's forward interpolation method, we have the Newton's backward interpolation method, we have the Lagrange interpolation method, and finally we have the binomial expansion interpolation method. Now, how do we tell which of these methods to use to solving any problem given to us? Whenever a problem is given to you in numerical methods which involves interpolation, there are 3 key things you need to understand first before you can apply any of this formula. The first thing to understand is the consistency of the interval. What is an interval? Interval simply means the distance of separation between 2 successive arguments. For instance, my arguments here we have 2, 3, 4, 5, and 6. Now, we said interval means the distance of separation between 2 successive arguments. So it is usually the final argument minus the initial argument, final argument minus initial argument, and so on. So if I do 3 minus 2, I will simply have 1. If I do 4 minus 3, I will simply have 1. If I do 5 minus 4, I will simply have 1. If I do 6 minus 5, I also have 1. So you see that the interval is consistent. The distance of separation between them is consistent. And that interval is denoted by the letter h. It means h is equal to 1. So if the interval is consistent, then we are going to be employing either the Newton's forward interpolation method or the Newton's backward interpolation method. That is the first thing to understand, the consistency of the interval. Okay, but if the interval is not consistent, let's take a look at this table underneath here. Now, if you take a look at this table, you find out that the interval is going to be 2 minus 4, which is negative 2, 6 minus 2, which is actually 4, 7 minus 6, which is 1, 9 minus 7, which is 2. So in this case now, the interval is not consistent. Rather, it is jumping. When you have a situation where the interval is jumping, then the only method you can employ to solving this interpolation problem, let's say you're asked to interpolate a certain value. Since the interval is jumping, then you can only employ the Lagrange interpolation method. okay, you can only employ the Lagrange interpolation method. So that is the first thing to consider, the consistency or the inconsistency of the interval. That tells you whether you're using the Newton's method or you're using the Lagrange interpolation method. Okay, the second thing to consider when solving numerical problems involving interpolation is the nature of the table. The next thing to consider is the nature of the table. Now, we have what is called the backward table and we have the forward table. Now, excluding the table of the argument and the entry, which is this x and y, the table that contains these actual numbers, the numbers of the argument and numbers of the entry, if we count these columns, we have 1, 2, 3, 4, 5 columns containing actual numbers. So, which means if I bisect this column into two, this is going to be my mid column. Okay, this is going to be my middle column. If this table is being bisected into two, that means the third column becomes the midpoint of the table. So I have to move 2 steps forward to get to the middle. I have to move 2 steps after the middle to get to the end of the table. Now, what is then the forward table and what is then the backward table? Now, the table of values directly forward to the mid table is called my forward table. So, which means this table 2 and 3, or this column 2 and column 3, directly forward to the middle table is called my forward table. So that is my forward table. Okay, that is my forward table. Whereas the table of value directly after the midpoint of the table to the end of the table is called my backward table. So from here to this point, okay, from here to this point is called my backward table. That's called my backward table. So keep this in mind. When you pick out the middle of the table of values directly forward to the middle table is called the forward table, whereas the table of values directly backwards or after the middle table is called the backward table. Now, why is this so? This helps us to tell which of the Newton's interpolation method to use, because as can be seen here, the first two is Newton's forward interpolation method, Newton's backward interpolation method. Now, how do we use the Newton's forward or backward interpolation? Now, let's say we're asked to find the value of y when x is 2.5 as given earlier. You observe that 2.5 lies between 2 and 3. And 2 and 3 falls at the forward table, which means automatically you're going to be employing the Newton's forward interpolation method to solving this problem. But if you're asked to find the value of y when x is 4.5, you observe that 4.5 is moving directly from the middle to the end of the table. So which means 4.5 falls at the backward table. And as such, you're going to be employing the Newton's backward interpolation method to solving this problem. So, two key things I've mentioned: the consistency or the inconsistency of the interval is the first thing to pay attention to when solving numerical analysis problems. If they are consistent, then you can use either the Newton's forward interpolation method or Newton's backward interpolation method to solve. But if the interval is not consistent, then you make use of the Lagrange interpolation method to solve. Again, you understand the nature of the table, whether it is forward or it is backward. So for a given value of x which you are to interpolate, if it lies at the forward table, it means you're going to make use of the Newton's forward interpolation method to solving the problem. But if it lies at the back of the table, which is the end of the table, then it means you're going to be employing Newton's backward interpolation method to solving that problem. Now, another thing to pay attention to, which is the final thing I'm going to talk about here, to pay attention to is the value of the entry. If there are missing values at the entry, then the only method you can employ is the binomial expansion interpolation method. When there are missing values at the entry, the only value to employ is the binomial expansion interpolation method. Okay, let me show you an example. So I have a table here already. So as can be seen on this table, these are the values of the argument and these are the values of the entry. But you observe that some certain values of the entry are missing. we have two values of y missing. In that case, you're not paying attention to the nature of the interval, okay, or whether it is a forward table or a backward table. No, all you're paying attention to at this point is the only method you're going to be using to solving this problem is the binomial expansion method, since we have missing values. So the binomial expansion method is majorly used to determine the missing values of the n3. All right. Now, having talked about the types of interpolation and interpolation themselves, let's now examine this table once more. Now, the table of value, the very first value of x is called x naught. Okay, so this value of x is called x naught. The next value is called x1. The next value is called x2. This is x3, and this is x4. So most times x4 can also be called xn, which indicates the last number of the arguments, okay, whereas s0 indicates the first number of the arguments. So in this case, 2 is x0, and 6 here, and 6 here is xn or x4. But then after x0, the next is x1, x2, x3, and x4. But you can also call this xn, which indicates the last value of the argument. Similarly, the very first value of y here is called y0. Okay, second value here is called y1. Third value here is called y2. The fourth value here is called y3. And the final value here is called y4, which can also be called yn. Yn simply means the last number of the n3. Now, having examined this, let's now talk about the formulas which are required to solving these problems. The Newton forward interpolation formula, backward interpolation formula, the Lagrange interpolation formula, and the binomial expansion interpolation formula, and how we can apply them to solving interpolation problems in numerical analysis. Okay. The Newton's forward interpolation method can be given by formula as y equals y0 plus u over 1 factorial multiply delta y0 plus u multiply u minus 1 over 2 factorial multiplying delta squared y0 plus u multiply u minus 1 multiply u minus 2 over 3 factorial times delta cube y0 plus u multiply u minus 1 multiply u minus 2 multiply u minus 3 all over 4 factorial multiplying delta fourth y0, and it continues like that as a series up to u multiply u minus n plus 1 all over n factorial multiply delta n y0. Okay, so this simply means that you can only stop where the difference table stops. So we are going to be coming to difference table much later in this video. Okay, but then how do you find u? U can be found as u is simply equal to x minus x naught all over h, where x is the value to be interpolated. So when I said earlier, if x is 2.5, find the value of y, that x is the value to be interpolated. 2.5 in that table is what we're interpolating. So x stands for the value to be interpolated, whereas x naught simply means the very first value of the argument as explained earlier. Okay, s naught simply means the very first value of the argument, and h here stands for what? The interval. H stands for the interval. So this is how you find u. Now, if you take a look at this table, you're seeing y0. I explained this earlier as well. Y0 simply means the very first value of the n3 in the table. Let me pull up the table once more. So this is my y0. The very first value of the n3 is called y0, whereas the very first value of the argument is called x0, which are the very first values of the independent variable, okay, x. So this is x0, and the very first value of y is called y0. Okay, now if you take a look at the subsequent values in the formula, you're going to see delta y0, delta squared y0, delta cube y naught, delta fourth y naught, and it continues like that. This delta y naught or delta squared y naught are called the difference in values of y, and this difference is obtained from the difference table. So usually after obtaining your u, of course now it's easy to find u. If you are given the value of x, you can easily find u, and after obtaining u, y naught can also be found from the table. Then you have to find these differences: difference in y naught, double difference in y naught again, triple difference in y naught, and then it continues like that. So which means, so in order to obtain these values, you have to plot what is called a difference table. Let's take a look at what a difference table looks like. Okay, so this is what a difference table looks like. A difference table is simply a table plotted to obtain successive difference in the values of y until only one value of that difference is left on the table. A difference table is simply a table plotted to obtain successive difference in the values of y until only one value of that difference is left. So the end of that difference tells us where we are going to be stopping the Newton's forward interpolation formula. Okay, if the difference stops at delta cube y naught, then we end our formula here. If the difference stops at delta fourth y naught, then we end our formula here. If it stops at delta fifth y naught, then it means we have to extend this formula by attaching here u minus 4 all over 5 factorial multiplies delta 5 y naught. So it continues like that. Okay, now let's take a look at this table. This is actually a table of the first values given here. As can be seen, these are the arguments or the values of x. We have 2, 3, 4, 5, 6, and these are the values of y. So we have plotted them out here. So how do you form your difference table? It's simple. You find the very first difference of y, that is called delta y, which means the first difference in y. And to obtain this, it means difference between successive values of y. So it means the forward minus the previous, forward minus the previous, forward minus the previous, and so on. So we have here 100 minus 70. This gives us the first difference in y. 100 minus 70 is 30, and you're going to be writing that difference in between 100 and 70. So you call this 30. Be very careful, it is written in between 100 and 70. The next difference is 180 minus 100, also written in between the two of them. Okay, so 180 minus 100, this simply gives us 80. So this is also what among the first difference. Next is 190 minus 80, also written in between the two, and 190 minus 80 simply gives us 10. Next is 290 minus 190, that simply gives us 100. Okay, so that's our first difference. So you do this until the difference values remains only 1. So since we have 1, 2, 3, 4, we keep on subtracting until it remains 1. So we are going to perform another difference. Okay, so we simply perform another difference, and this time around the second difference is called delta squared y. This is now the second difference, and it still follows the same procedure, subtracting successive values of now the difference obtained, or the first difference obtained. So we have 80 minus 30 written in between the two of them, and 80 minus 30 will simply give us 50. Next you have 10 minus 80 written in between the two of them, and 10 minus 80 gives us negative 70. Next we have 100 minus 10 written in between the two of them, and 100 minus 10 simply gives us 90. Then you have this. So you see that now we are down to what? 3. We keep on doing this until we are down to only 1. Okay, so we plot. So we carry out another difference now. Now the next difference here is called delta cube y, which means the third difference table. Okay, which is the third difference. Now the third difference, just like in the previous one, still remains Now this becomes negative 70 minus 50, and you write the answer in between the two. So negative 70 minus 50 simply gives us negative 120. You have negative 120. Next you have 90 minus 70. 90 minus negative 70, and that will simply gives us 160. So you also write that in between the two you have 160. Okay, so since we are now down to 2, then we'll also subtract till we are down to only 1. Okay, so now we are left with only 2. Then we'll also find the difference. Now this will give us what? The fourth difference. So this is now delta 4y. Okay, so the fourth difference also the last minus the previous. So you have 160 minus 120. Okay, 160 minus 120. Negative becomes plus, so that simply gives us 280. So the difference is now written at the middle, which is 280. Okay, that becomes the difference. Now the table of values as can be highlighted. Okay, these values, the very first values of all from here, the very first values of all from here is what is called the leading forward differences, and this is what we are going to be using to in the Newton forward interpolation. These values are called the leading forward differences. Okay, all right, so these values are called the leading forward differences. The values at the upfront are called the leading forward differences, whereas this is called y naught, already established. The very first value of the entry is called y naught. This is called delta y naught, as can be seen from the formula. Okay, so in the formula we have delta y naught. This is called the first difference, is called delta y naught. Next you're seeing delta squared y naught, which is this second difference, is called delta squared y naught. This is called delta cube y naught, and this is called delta fourth y naught. Okay, so this is delta y naught, this is delta squared y naught, this is delta cube y naught, and this is delta fourth y naught. These values, and these values are called the leading forward differences, whereas 70 here is called y naught. So using the Newton's forward interpolation method, this is how you find your what differences. Your y naught is already in the table. Okay, so y is called y naught from the formula. The first difference is called delta y naught, as can be seen. The second difference is called delta squared y naught, which is this. Third difference is delta cube y naught, which is this. So depending on where the table ends, like for now this table ended at delta fourth y, that's the fourth difference. So which means we are going to be killing our formula here. We stop it here. So if you put in these values into here, find the value of u, then we can be able to simply solve this problem. It's as easy as that. Since we know the values of this now, all we need to find is u. So let's say for instance, as we are asked to find the value of y when x is equal to 2.5, then we know that x naught, being the first value of the table of x, is equal to 2. That means u can be found here. Okay, that means u can be found here simply as x minus x naught. X is the value to be interpolated, which is 2.5, minus x naught is the very first value of argument in the table, which is 2. So x naught is equal to 2 all over h is the interval already established, which is 1. 3 minus 2 is 1. 4 minus 3 is 1. So divide by 1. So this is actually what? 0.5 divides 1, which remains 0.5. So you see, we now have the value of u. We know the value of these differences. Then we can simply plug in this formula and obtain the value of y. Okay, that becomes the value of y when x is equal to 2.5. So that's how you employ your Newton's forward interpolation formula to solving a problem. Okay, don't worry about this. In the next video, we're going to be doing more problems involving the Newton's forward interpolation and backward interpolation method. This is just an introductory video. This is just an introductory video to build us ahead of the calculation video. Alright, so having explained the Newton's forward interpolation method by formula, let's now look at the Newton's backward interpolation method formula and how to use it. Now, by formula, the Newton's backward interpolation method can be represented as y equals yn plus v over 1 factorial multiplies delta yn minus 1 plus v multiply v plus 1 over 2 factorial multiply delta squared yn minus 2 plus v times v plus 1 times v plus 2 over 3 factorial multiply delta cube yn minus 3 plus v times v plus 1 times v plus 2 times v plus 3 over 4 factorial multiply delta fourth yn minus 4, and the series continues like that. The formula continues like that in form of a series up to v times v plus n minus 1 over n factorial multiply delta n y naught. Okay, now in the previous formula for the Newton's forward interpolation formula, you see this is y naught, which is forward, which means the very first value of y in the table. But now we're talking about the backward interpolation formula, so we consider yn, which is the last value of y on the table. So I explained this earlier, okay, that yn simply means the last value of the entry or last value of y on the table. Okay, now how then do we find v? V can be solved or given mathematically as x minus xn all over h. So when we talked about the Newton's forward interpolation formula, we said u is x minus x naught because it is forward. So x naught consider the very first value at the forward table. But now v is taken simply as x minus xn. Xn simply means the last value of x on the backward, which is at the backward table. Okay, xn simply means the last value of x, which is at the backward table, and once again h remains the interval. Okay, now we need to now find what are the values of delta yn minus 1, delta yn minus 2, delta yn minus 3, delta yn minus 4, and so on. What are these values? These values are also obtained from the difference table when we consider the backward or leading backward difference. So let's fall back to the difference table we just did. Okay, we just formulated a difference table, and I said the leading values are called the leading forward differences. So these first values are called leading forward differences. That means to obtain the backward differences, it has to be from here, directly opposite. So backward differences are simply measured from here, from this point. Okay, from this point, okay, so this point, this becomes our backward differences. All right, so this becomes our backward differences. So including also the very last number, including also the very last number. Now remember, the value of y or the last value of y is termed as yn. So this is yn. The next value of y at the difference is called delta yn minus 1. This other value is called delta yn minus 2. This other value is called delta yn minus 3. Finally, this is called delta yn minus 4. Okay, so it's as simple as this. The very last numbers that connect to the first, or very last differences that connect to the first, are called the leading backward differences, whereas these are called the leading forward differences. It's as simple as this. So having found this value from difference table, all you need to do is simply plug them into the formula. Okay, we know what yn is, we know what yn minus 1 is, we know what this is, and since the table ends at delta fourth, which is the fourth difference, it means we are killing our formula here. But if the table extended up to the fifth difference, it means we have to extend this by attaching what? V plus 4 over 5 factorial multiply delta 5 over yn minus 5 and so on. Okay, whereas to find V is simple. Remember the value we are interpolating earlier, we said this is 2.5, so it means x is 2.5. Then xn simply means the last value of x in the table, which is this. So this is my xn. Sn is equal to 6. The very last value on the table is 6. So it becomes 2.5 minus 6 all over h. H is the interval between the two. So that is if we are actually solving this problem. But this is just to explain what the difference table is all about and what is the forward differences which we've obtained so far and the backward differences which we've obtained so far. Okay, so that is the case of the Newton's forward or backward interpolation method. Now let's take a look at the formula of the Lagrange interpolation method. So remember I said that before you can make use of the Lagrange interpolation method, it means that the interval must be jumping. Okay, so we are going to be considering this table. It means the interval must be jumping before you can employ the Lagrange interpolation method. Now here is the formula of the Lagrange interpolation method. Now let's see how we are going to be applying the Lagrange interpolation method. So this is the formula. So by formula, this is the Lagrange interpolation method. Now, when we are at column x0, which is the very first column of the arguments, we don't consider s0 at the numerator, we only consider it at the denominator. When we are done with x0, then we jump to x1. Once we are at column x1, we don't put x1 at the numerator, we only put them at the denominator. The formula just repeats itself, but we are omitting each of the columns we are jumping to and putting them at the denominator. We are simply omitting them at the numerator. When we are at column x2, we don't put x2 at the numerator, we only put them at the denominator. So let's explain this formula. Now we are at column x0. It becomes x. X, remember, is a value which we are interpolating. So we have x minus x1. We have skipped x0 because we are at column x0. It becomes x minus x1 times x minus x2 times x minus x3. It continues like that up to x minus xn, which means the total number of x we have on the table. Now, multiply by what? Y0. Multiply by y0 being the very first value of y at the table. Okay, now divide by, since we are at column x0, then we use x0 to subtract all the values of x on the table. So divide by x0 minus x1, x0 minus x2 times x0 minus x3 times x0 minus x4 up to the total number of x we have, which is x minus xn. Okay, now plus, since we are done with x0, we now jump to what? X1. If we're at column x1, then we'll completely avoid x1 at the numerator. So we have now x being the value we are interpolating minus x0 times x minus x2. So you see that we have skipped x1 at the numerator and jumped straight to x2. Okay, so it continues like that times x minus x3 up to x minus xn, total number of x we have on the table. Okay, now multiply by y1. Y1 simply means the value of y under x1, the column that we are directly on. Now divide by, so we bring in x1. Now x1 now subtract every other values of x at the denominator. So you see how this formula works. The value, the column that we are actually on, we don't put those values at the numerator, we only put them at the denominator. So at the denominator we have x1 minus x0 times x1 minus x2, it continues like that, times x1 minus x3 times x1 minus xn, total number of x we have on the table. Okay, having done with this, now we are jumping from x1 to what? Column x2. So we have plus, it becomes x minus x naught times x minus x1 times x minus x3. So you see that we have omitted what? X2 at the numerator, since we are now at column x2. Okay, so the formula continues times x minus xn, which means total number of x we have on the table. And since we are on column x2, multiply this row, or multiply this particular row by what? Y2. Then divide by x2 now comes under at the denominator. So it becomes divide by x2 minus x1. So you use x2 to subtract all the values of x we have on the table. So it becomes x2 minus x naught times x2 minus x1 times x2 minus x3 times x2 minus x4 times x2 minus xn, which is the total number of x we have on the table. Okay, it continues plus, now we are at column x3. Since we are at column x3, we simply skip x3 at the numerator. It becomes x minus x naught times x minus x1 times x minus x2 times x minus x4. So we've skipped x3 because we are at column x3, so we don't repeat x3 at the numerator. Okay, now it continues like that up to x minus xn, total number of x we have on the table, times y3. Since we are on column 3, multiply by y3, divide by, now we put in x3 at the denominator. So we have x3 minus x naught times x3 minus x1 times x3 minus x2 times x3 minus x4, okay, times x3 minus up to x and total number of x we have. So the formula continues like that. Okay, it continues up to what? X minus xn minus 1 over xn minus xn minus 1 multiplied by y and total number of y, and it continues like that. So let's take a look at this table. This is the table for the Lagrange. Because the interval here is jumping, so we simply say when we are at column x naught, we don't repeat this at the numerator. So all we need to do is, if we're asked to interpolate the value of x, let's say when x is equal to 4.5, let's find the value of x. If we are to do this interpolation, then it means x is equal to 4.5 from the formula. So you take a look at the formula. It becomes x is 4.5. So we are using the value we are interpolating to subtract the remaining values of the argument on the table. Okay, so since we are on column 1, we are not going to be touching x naught. It becomes 4.5 minus x1, which is 2, times 4.5 minus x2, which is 6, times 4.5 minus x3, which is 7, times 4.5 minus x4, which is 9. Okay, now multiply by what? Y naught, and y naught is simply what? 50, the very first value of y under x naught, since we're on column x naught. Now divided by, remember, let's pull out the formula once more, divided by what? X naught minus x1. So we are using the column now, x naught, to subtract every other values of x. So it becomes x naught minus, which is 4 minus 2 times 4 minus 6 times 4 minus 7 times 4 minus 9. That's it for that row. Plus, then you move now to x1. So since we move to x1, we don't consider x1 anymore at the numerator. It becomes x minus x naught times x minus x2. We skip x1, so it becomes 4.5. So it becomes 4.5 minus 4 times 4.5 minus 6. So we simply skip x1, times 4.5 minus 7 times 4.5 minus 9. Again, multiply by y1 this time around, which is simply 80. Divides by, so we'll use the value of x1 now to subtract all the values of x. Divide by what? 2 minus 4 times 2 minus 6 times 2 minus 7 times 2 minus 9. So it continues like that till we exhaust the values of x on the table. Okay, so like I said, in the next video we are going to be solving more examples that involves all of this, so no need to hurry. You're going to be seeing a practical example of all this everything we've said here in the next video. Okay, so the final is the binomial expansion method as explained earlier. You can only employ the binomial expansion method when there are missing values of the entry. So as said earlier, you only consider the binomial expansion method when there are missing values at the entry. Okay, you only consider the binomial expansion method when there are missing values at the entry. So remember the formula of the binomial theorem. Y minus 1 to the power of n is equal to 0. This is the formula of the binomial expansion theorem. So this simply means n there means the total number of values of y that are known. Okay, so we have 2 values of y that is known. This simply implies n is equal to what? 2. Therefore this formula becomes y minus 1 to the power of what? 2 is equal to 0. Then you simply employ the Pascal's triangle to find this expansion. Y minus 1 to the power of 2 is equal to 0. So let's do a rough sketch and see. Now we are to find y minus 1 to the power of 2 is equal to 0 from Pascal's triangle. Remember the Pascal's triangle, you start from 1, then it becomes 1 and 1. Then you have, again, pull down this one here. Then 1 plus 1 gives us 2. Then 1 plus 0 gives us 1. Again, you pull down this one here. Then 1 plus 2 gives us 3. 2 plus 1 gives us 3. 1 plus 0 gives us 1. It continues like that. This is the Pascal's triangle. But the one that contains second power 2 is simply 1, 2, 1. So which means we are going to be effecting 1, 2, 1 to expand this. Okay, so how do you expand this? We are simply making use of 1, 2, 1 to carry out this expansion. So that simply means we have y minus 1 to the power of 2. So you have y to the power of 2. Okay, not forgetting. Okay, let me just break this down a little bit. This is 1. You start with the 1 times y to the power of 2. And then negative 1 times negative 1 is now dropping, starting from 0. So y is starting from 2, negative 1 is starting from 0 and increasing, whereas y is starting from 2 and is decreasing. You have plus, again, the next value there is 2. You have 2 times y to the power, now this is y to the power of 2, y will now drop to the power of 1, again, times negative 1 will now increase by 1. It was 0 here, it becomes 1 plus, finally you have 1, again 1 times y is now going to drop from 1, it becomes 0 times negative 1 to the power of negative 1 will now increase by 1, it becomes what? 2. So you observe we have 1, 2, 1, which is the second power for the Pascal from the Pascal's triangle. Okay, so this simply means that of course, y squared times negative 1 to the power of 0 is 1. Y squared times 1 simply gives us y squared. Again, we have negative 1 to the power of 1 remains negative 1. Negative 1 times y to the power of 1 remains negative y times 2. This gives us negative 2y. Okay. Plus now you have here negative 1 to the power of 2 is simply positive 1. Positive 1 times y to the power of 0. Y to the power of 0 is 1. So 1 times 1 gives us 1 times 1 again is 1. So you have plus 1. And this is equal to 0 because we said y minus 1 to the power of 2 is equal to 0. So this is the binomial expansion for this given value. So with this, you can now, so you have to now rewrite this. Instead of y to the power of 2, this becomes y to the to base 2, okay? It becomes y to base 2, which means the second value of y on the table. So if you take a look at this table, this is our y2. Okay, no, this is our y2, the missing value, sorry. So remember, this is y0. The very first value of y is called y0. Second value of y is times as y1. the third value is termed as y2. This is y3 or yn. So this is now what, instead of y squared, you now rearrange the order. It becomes y2 minus 2y. Now this is automatically saying y to the power of 1. So you rearrange the order. It becomes y to base 1 plus 1 equal to 0. So all you need to do is plug in the values of y2. Y2 is what we are looking for, unknown. Then we have y1. Y1 here is simply what, 175. So that simply means we have the value of y1. This equation now can be written simply as y2 is unknown plus, minus 2 times 175 plus 1 equal to what, 0. So you're going to have that y2 minus, let's obtain 2 times 175. So 2 times 175 gives us 350 plus 1 equal to 0. This simply implies y2 minus 350 plus 1. This gives us negative 349 equals 0. So you see, with this you're able to find what, the value of y2 to be equal to 349. So it goes as far as this. After expanding and you obtain this, now be quick to remember that you're not going to be keeping it as y squared. You rather bring down the power to a base. It becomes y2 minus 2y1 plus 1. So if you're able to obtain this, we have now been able to find the value of what, y2. Next is to find the value of y3. Since you want to find the value of y3, what do? You simply rewrite the binomial expansion formula obtained. So when you started from y2, it dropped to y1 and you had y1 here. Remember that this one can also be written as what, y to the power of 0. Y to the power of 0 can be called 1. Of course, any value to the power of 0 is simply taken as 1. So from this order we've said here, you bring down the powers. So it means y squared becomes y2. That means y to the power of 0 can simply be taken as what, y to base what, 0. Now we want to find y3. We start again by rearranging this equation. So it falls from 2 to 1 to 0. That's what it means. It falls from 2 to 1 to 0. So that means for y3, we are going to have y to the power of 3. It will now fall. This becomes minus 2 times y to the power of 2, plus y to the power of 1 equal to 0. Remember I said that this 1 simply means y to the power of 0. So it moves in decreasing order, y squared, y1, and then y0. So which means if I have to find y3, it becomes y cubed times it becomes y cubed minus 2y squared plus y1. So it moves in decreasing order, 3, 2, and 1. And if we rearrange this, it simply becomes what, y3. Simply bringing down this power, it becomes y3 minus 2y2, plus y1 equal to 0. And if you take a look at the table, we've already obtained the value of y2. We know what y2 is, we know what y1 is. Then we can simply plug in into this equation and obtain the result for y3. So y3 automatically becomes, so y3 is now going to be minus 2 times y2. Y2 is the value we obtained here, which is 349, plus y1, and y1, as can be seen from the table, is simply 200. So plus 200, and this is equal to 0. So plus or minus, you can have y3 to be equal to, let's punch everything all together. So you have 2 times 349, plus 200. This gives us so this gives us 498. So y3 is actually 498. So this is how you find the values or the missing values on a given table using the binomial expansion method. So that's it for this video. We've explained the four key interpolation methods, given their formulas and how you can apply them to solving problems. In the next video, we are simply going to be employing everything we've learned here to solve a real problem. I'm sure you want to be a part of that video, so do well to please smash the subscribe button, like this video, comment nicely and share to your friends. I will see you in the next video. Thanks.